thought it might be helpful to go over some of the clicker questions that we got some questions about this week. So the first one is this one where you have two choices with your car: either hit a head-on collision or swerve into a massive concrete wall. And the key here is that the head-on collision is with a car that's identical to you, the same car, the same speed. And so in this case, it makes no difference. And the way we reasoned through this in class is we went through the impulse momentum theorem. And so just for here, I'm just going to say let's just assume that the speed is 30 meters per second, not miles per hour, so it's easier to deal with for us. Okay, so we start with an initial speed of 30, and we end with 0 either case, whether we hit the wall or we hit the car. And so the force we feel looks like this. And so since the force is the same, it makes no difference. Now, I mentioned in class that if you were to say hit something that had more momentum than you, this could be a different story. And so let's suppose instead you hit a truck. The truck is going at the same speed, let's say it's 30, but the truck is twice as massive as you. So because this is a collision, we can conserve the momentum. And so what I said here is the final momentum, assume the two objects stick together. So the total mass is 3. That's 1 m for your car, all right, and then a 2 m for the truck. And then over here, initially, the mass of the car times your speed of 30, positive, and then the mass of the truck, 2 m, times its speed, negative 30. If you go through, first of all, you can cancel out these m's, and then you can go through and solve for the velocity. And so now in this case, your velocity afterwards is moving in the negative direction. So this is where the difference is. In the first case, your car just comes to a stop, but now the collision moves you backwards, and so you have a greater change in momentum. And if we put this into equation form, so here's the first case. Okay, the first case when you hit the wall, all right, so your speed is 30 initially and then goes to 0. So the force is your mass times a change in velocity of 30. Now over here, if we look at the truck, so your initial velocity is 30, but your final is negative 10. And so if we calculate this, your change in velocity is now 40, and so that makes your change in momentum bigger, which means the force would be bigger. So because you're actually being pushed backwards after the collision, it's a greater change in momentum, a greater force. And so that's why in some cases, a head-on collision can be worse. Another problem that was tricky, very tricky, was this idea of we throw two balls, one bounces off and one sticks. And we wanted to know which one will make the box move faster afterwards. And the way we talked about this in class is we know that when the ball bounces, it delivers more impulse. And so impulse equals the change in momentum. And so because of that, we know that this guy will move faster, because if it gains more momentum, it'll have a bigger speed. But let's think another way we can try to think about this, and that'd be being a little bit more mathematical. So we know that during these collisions, the momentum is going to be conserved. All right. Now I'm just going to say, so here's our equation. So here's the momentum of the ball initial. So that's the same in both cases. The initial momentum is the same in both cases. Now afterwards, I said here's the momentum of the box, P sub 1, and I said here's the momentum of the ball final. Now we don't really care what that is, but we know the key is that it's a negative sign. Okay, it's moving backwards. If I look at the other case, okay, the same kind of setup. So the initial ball is the same momentum as the initial case, as the case over here, and then here's the momentum of the box, P sub 2. And let's just say that just for making this easier, that the momentum of the ball in this case is the same, just in a different direction. Okay, we know that this ball is going forward, and so it should be a positive sign over here instead of a negative sign. Then if we solve for these, you can see that P1, it's the addition of these two, P2 is the subtraction of these two. So it doesn't matter what this actually is here, but because it's being added here and this is being subtracted, remember this one, this piece here is the same in both cases, we know that P1 must be bigger than P2. Okay, so that's just another way to think about this. And so box 1 has to be faster. The last one I want to talk about was this bomb at rest that explodes into two fragments. We asked about which one has more kinetic energy afterwards, and it works out that the more massive fragment has less kinetic energy than the smaller fragment. Okay, and so let's look at this. So the way we reasoned through this in class, we said, well, if the smaller mass, okay, because it's a collision, so the two pieces in this explosion have to have the same momentum. So the smaller mass has to have a greater velocity, and in the kinetic energy equation, velocity is squared. So if I have a bigger velocity, since that's squared, it has a bigger effect, and the kinetic energy will be larger. And we also showed this equation here, that's a little trick equation for the kinetic energy, and this says that the smaller your mass is, the bigger your kinetic energy is. Now with this one we can also be a little more mathematical. So here's an example problem we did in a few pre-lectures ago where we had a bomb that exploded into a 30 kilogram piece and a 15 kilogram piece, and we're told that this speed was 10. And we wanted to, in this problem, go through and find what the speed was. So we did conservation of momentum. So 15 times 10 to the right and plus 30 times v to the left, and we were able to go through and solve for that in the left. And we got that it was -5 meters per second. And if we set that up into our equations and just solve for the kinetic energy in the two cases, so plug in the stuff for the kinetic energies in the two cases, you see that the smaller one does come out to be bigger, just like expected. Okay, hope that helps.